our big read for this week. You're in your literature anthology, your big reading book. You should have it open on page 62. Now, if you want to become a great reader, you got to follow along as I read to you. Use your pointing fingers. Read it in your mind. That's how you become quicker and quicker at them. All right. Our genre is narrative nonfiction. Our essential question this week is, how can science help you find out how things work? A crash course on force and motion. Now, it's pretty cool because it's written like a cartoon, so we can see a lot of interesting pictures to help us. About Max. Real name, Max J. Axiom. Hometown, Seattle, Washington. His height is 6'1". His weight is 192 pounds. His eyes are brown, and hair is none, which is kind of a joke. It's kind of funny. Super capabilities. He's strong intelligence, able to shrink to the size of an atom. Sunglasses give him X-ray vision. Lab coat allows him to travel through time and space. Origin. Since birth, Max Axiom seemed destined for greatness. His mother, a marine biologist, taught her son about the mysteries of the sea. His father, a nuclear physicist and volunteer park ranger, schooled Max on the wonders of the earth and sky. One day, on a wilderness hike, a mega-charged lightning bolt struck Max with blinding fury. When he awoke, Max discovered a newfound energy and set out to learn as much about science as possible. He traveled the globe, earning degrees in every aspect of the field. Upon his return, he was ready to share his knowledge and new identity with the world. He had become Max Axiom, super scientist. If you've ever gone on I believe it's the Batman ride or the Superman ride at Six Flags Great America, they actually have a whole bunch of these characters on things, big posters on the wall as you're waiting in line so that you can read them, and Max Axiom is one of them. All right, force that move us. Super scientist Max Axiom jumps right into the world of force and motion at an amusement park. What a perfect day. Squawk! I think the bird made that sound. Excuse me. Even though everything feels turned upside down, spinning, flying, jumping, and falling are just some of the amazing ways to move. But there's a lot of science behind the zoom, zoom, zoom around us. So the bird really wasn't upside down. Max was upside down. He had just bungee jumped at the amusement park. In fact, the world is full of all kinds of motions. Everything that moves needs a force to get it moving. Back for another jump already? You bet. A force is a push or a pull on an object. Bungee jumping depends on the force called gravity. It pulls objects towards each other, and it keeps us on the earth. Gravity is the reason I fall down, not up or sideways. Could you imagine if gravity pulled you up? We'd all be banging our heads on the ceiling all day. But no, God gave us gravity, and it keeps things on earth. Whew! Moving can be thrilling, but I need a break. Snap, snap. Hey, Rosita, what are you doing here? Hello, Max. I'm taking notes for a physics class I teach. Why are you just sitting there? Is something wrong? Once I sit, sometimes it's hard to get moving again. But once I get going, I often can't stop. Now, they're really talking about a law of motion here. We'll read more about it in a second. That's inertia for you. Remember from our worksheet earlier. That's inertia. An object at rest tends to stay at rest. An object in motion tends to stay in motion. That's Newton's first law of motion. A still object needs a force to get it moving. Likewise, a moving object needs a force to change its direction, slow it down, or to make it stop. For instance, now here comes the example. Remember, our context clues will help us learn things by examples. For example, inertia keeps that stroller rolling. Whee! So the dad had let go of the stroller. It started rolling down the hill, and now the dad's chasing it, but it's not going to stop by itself. Something's got to stop it. Now, there's a few things that could stop it. The dad could grab it, which we see in the next picture, or it could run into something, or it could flatten out on a flatter surface, or it could run into the grass, and the grass would cause friction to slow it down. Until another force comes along to stop it. The kids are like, we want to crash. To clear your inertia, you just need a little push. And so now this Rosita gives him a little shove to get him going. Come on, let's go ride the roller coaster. Let's move. Here we go. I feel like I'm being pushed to the back of my seat. That's inertia. When the ride starts, your body is at rest. When the chair moves forward, your body wants to stay at rest, but the chair moves into you. The chair's forward motion makes it feel like you're being pushed back in your seat. Wow, how does this roller coaster go so fast? The force of gravity is increasing our speed because it's pulling them down. Speed is how fast we are going at any given moment. Acceleration is how much speed we pick up as we go down the hill. Acceleration causes us to move more quickly at the bottom of the hill than we did at the top. The bar digging into my stomach must be inertia too. You got it. Now look at, they're coming to a stop. And so the car's coming to stop, but the girls are still moving. So they're banging into that bar. The ride comes to a stop, but your body wants to keep moving. The lap bar applies a force that keeps you from flying out of the car. So the lap bar stops us from continuing forward on the roller coaster. What keeps that stone from staying in motion? So we're saying things that are moving are going to keep moving, so he kicks it, but it looks like it's kind of slowing down. Big bump, middle, little. Excellent question. You can't see it, but a force called friction stopped the stone. Friction happens when two surfaces rub against each other. On Earth, gravity and friction work together to slow things down and make them stop. Now there's an interesting fact down here. In space, there's no friction. If you kick the stone, it would keep going and going and going. That's why astronauts are tied to the space station when they do spacewalks. Otherwise, they would just float away. Brakes on a roller coaster use friction to slow us down too. Come on, I'll show you. Each roller coaster car has two brake fins. Those are the parts underneath it. Attached to its underside. As the car approaches the station, these fins slide between two sets of brake rails. See there, right here? When the fins go through there, the brakes slow them down. I see. When the brake rails squeeze against the fins, friction stops the car. I had a great time, Rosita, but I've got to run. My nephew's having his birthday party over at the Skater's Paradise. See you later, Max. Motion is a weighty issue. Juggling these bowling balls is wearing me out. So this guy's juggling bowling balls. This guy's juggling just little tiny balls. I don't know what that guy's so tired. Juggling is easy. The juggler on the right is tired because he uses more force to throw and catch these heavier objects. He's showing us Newton's second law, that the amount of acceleration that a force can produce depends on the mass of an object. Now, mass is actually how much matter it is. A lot of people think mass is how much something weighs. Mass is actually how much matter there is. What's mass, Uncle Max? Mass is the amount of matter in an object. The bowling ball has more matter in it than the tennis ball, so it feels heavier. Think about it. Which ball would be easier to juggle, Nick? Well, obviously the tennis ball. All right, gravitational pull. Weight is different from mass. Weight is determined by gravity's pull on an object. Each planet in our solar system has a different gravitational pull. If you travel to each of these planets below, your mass would always be the same, but your weight would be different. Multiply your weight by the number shown below each planet to find out how much you would weigh there. If you were 100 pounds on Earth, you would be 38 pounds on Mars. Okay, because Mars is a lot smaller, it's got less gravity, so it would pull you down less, so you'd only weigh 38 pounds. But if you went to Jupiter, you'd be a whopping 236 pounds, because Jupiter's so big, it's got a lot of gravitational pull to pull you down, which would make it seem like you are heavier. But you would still be you. All right. I have another way to think about Newton's second law. I need 2 volunteers. Pick me, pick me. I'll do it. I'm going to push both of them at the same amount of force on a level surface. Who do you think will accelerate faster? Johnny's bigger. He'll go faster. Jenny's an awesome skater. She'll win. Both of my arms are equally strong, so the amount of force will be the same. So you've got to have the same force if you want to do this test. Let's see who gets a faster start. So he gives them a push, and look, Jenny goes farther because she weighs so much less. Like the tennis ball, Jenny has less mass than Johnny, so then she gets a faster start with the same push. Johnny would need a stronger force to get moving as quickly. I'm like the tennis ball, and it's kind of funny that she's wearing yellow, right? Does that mean I'm a bowling ball? The kid kind of made a funny joke there. All right, Uncle Max, Jenny won the race on the flat surface, but I noticed that the bigger kids always travel faster than the smaller kids skating down the ramp. Sometimes having more mass can give you an advantage. There's our vocabulary word, advantage. Let's have Johnny and Jenny race again. In the last race, we wanted to see who would get a faster start. This race is for distance. I'm going to release you at the same time. We'll see who travels farther without pumping. Johnny's got it in the bag. No way, Jenny will beat him easy. What's your prediction? Well, I'm going to predict him because he's heavier, so that he should be able to accumulate more motion. Did you see that? Gravity pulls them down the ramp, but Johnny travels farther than Jenny. Max, what happened? I got a good start, but Johnny just passed right by me. Johnny's larger mass takes more force to slow down or to stop than your smaller mass. That'd be like if a little tiny bicycle banged into the side of the house. Probably wouldn't do much damage. Now you take a big semi and you smash it into the side of the house. It would probably do more damage because it would take more of the house to slow down a bigger object. Friction between your wheels and the ground was the main force slowing both you down. Johnny needed more friction to stop, so he traveled further. Time for cake. Remember, they were at a birthday party. I don't think these kids will let a little friction stand between them and chocolate cake. So that was our story on forces and motions. When you have a narrative nonfiction story, you're going to have lots and lots of facts. A good strategy when you're reading those facts is to reread any of the ones that you didn't get. God bless your day.